All right, let's pick up at the reciprocal function. Reciprocal. If you recall, the reciprocal function is just the function where it's a fraction. So that's why we call it the reciprocal function. If you recall, the graph of the reciprocal function is actually the first one that is not continuous because it is in two pieces. So you have the curve in quadrant 1 and the curve that is not. Okay. All right, that doesn't like me. There we go. So that is the sketch of the reciprocal function. All right, let's go down our list. First of all, the domain and range on this one are a little weird because, not to skip ahead, but this one obviously has asymptotes. So I have to say that it goes, like the domain goes from negative infinity to 0, but obviously there's not a point at 0. And then it picks back up on the other side of 0. It goes to positive infinity, right? Because it uses all of this side and all of that side, but not 0 in the middle. The same thing for the range. It's actually exactly the same. It goes from negative infinity until it hits that asymptote and then skips and then goes to positive infinity. So the domain and range, because again, it is discontinuous. This one actually has infinite discontinuity, like we talked about, I guess it was last week, because of the asymptotes. So this one is technically decreasing everywhere. Let's talk about that, but we, again, have to skip over the asymptotes. So as I explained in my Algebra 2 class, think of it as a roller coaster, right? So if I were here and going down the roller coaster, that's obviously going down. So it's decreasing from negative infinity to 0. But then this one has two parts, right? This one has two roller coasters, for lack of a better analogy. If I were here, because again, you have to go from left to right. So if I were up here and I'm moving to the right, again, I'm still decreasing. So it's also decreasing from 0 to positive infinity. Wow, look at the pattern. This one has origin symmetry. Origin symmetry. And let's see what else. It is not bounded. There are no maxes or mins. It does have asymptotes. It doesn't have any x or y intercepts, obviously, because the asymptotes are there. So let's list those. There's asymptotes on both the x-axis. I can spell. My brain's getting ahead of myself. Axis, which is the line y equals 0, and the y-axis, which is the line x equals 0. So those are the two asymptotes. And the end behavior, everybody's favorite. Here we go. So it's the limit as x approaches negative infinity, and the limit as x approaches positive infinity of the function. And again, this one's very similar to whenever we did the logarithmic and exponential, because like on the left side over here, it's not going up or down, it's flattening out at 0. And the same thing's actually happening on the right side. I can see that it's flattening out over here, so the limit is also 0. So I think I didn't miss anything. That is the reciprocal function. I did that one last year. All right, see, the next function are the sine and cosine functions. So sine, I'm going to do sine first. Cosine is almost exactly the same. Almost just wrote cosine. Of course, the difference is we know the wave is shifted, so that's going to be a little different. We'll talk about that. All right. We're going to get really well acquainted with this again this year. So if you recall, whenever we graph these, I'm going to actually put points on this one because of the x and y intercepts. But if you recall, this one actually goes through pi halves, pi, 3 pi halves, and 2 pi. And it goes, the max and min are, or the top and bottom, the range is +1 and -1. Whoop, whoop. And so this was a curve. And remember how this was just one period of the curve, one cycle. But we know that it kept going. It was a repetitive curve. It was a cyclic function, is what we called it. So the domain on this one is all real numbers. It uses all of the x's because it's going to continue going. But the range is not. This is a bounded function above and below. The range goes from square bracket, -1 to +1 square bracket, because there are points at those highs and lows. So -1 to +1 is the range. It is a continuous function. It's probably my favorite continuous function. It's so pretty. It is, okay, so it is technically decreasing and increasing on intervals for the whole thing. So we're going to table decreasing and increasing. That's a whole discussion. It's not symmetric anywhere. It is bounded above and below in both places, obviously, because it doesn't go above 1 or below -1. There are, like, the maxes are here. So I forgot my, see, I didn't write that down. So the maxes are, and the relative maxes, well, okay. That's another discussion too. We haven't got that deep into trig yet. So let's just say there are maxima at multiples of pi halves. So it's at the k pi halves. Okay, so let's do that, because, I mean, we could see here at a half. And then there are also mins at the same intervals, but at n, or not n, I used k, so let's stick with k. The k plus 2 pi halves. So just know there are maxes and mins at varying intervals. Let's stick with that. There are no asymptotes, and the end behavior we also need to talk about too, simply because it's not going up or down. It's not going anywhere. We'll hit that whenever we get to chapter 4. But for right now, the intercepts. Jesus. Okay. So the only y-intercept is the origin. But the x-intercepts, my brain's getting ahead of itself again. The x-intercepts we can see occur at the pi's, right? 1 pi, 2 pi, again on 3 pi. So the x-intercepts happen on the k pi's. Okay, so that's sine. So I'm going to sketch cosine, and honestly, the only difference between sine and cosine is pretty much your intercepts and your maxes and mins kind of flip-flop. So let me sketch that down here. Cosine. I don't know why I just made that so tall. I have no idea. Let's make it shorter. Okay, so again, we're going to kind of sketch this one. And it uses the same intervals. Pi halves, pi, 3 pi halves, 2 pi. But if you recall, this one actually starts at 1. It does not go through the origin. So one cycle of this function looks like this, right? And again, we know it actually keeps going. And so that's what's, it's just the same function, just shifted. So the domain on this one's still all real numbers. The range on this one is still from -1 to +1. It's still bounded in the same way, above and below. Okay, but again, what changes are the maxes and mins. So now we can see, like, the maxes are at 0, 2, the next one will be at 4, and then the mins are going to be at 1, 3, and so forth. So the maxes are at the 2 k pi's. And then the mins are at the k pi's. So the even numbers, the odd numbers, basically. The y-intercept on this one is the point 0 and 1. And the x-intercept on this one, so if you notice, like these go through the halves this time, right? So the x-intercepts are at the k pi halves. I think I hit on everything. Yes, because there are no asymptotes. Yep, I got all those. Sine, cosine. There we go. This one. The greatest integer function is the next one. So we talked about this one a little bit last year, and again, it kind of just pops up. The greatest integer function, if you recall, we also call it the step function because it looks like steps. And it depends on what program you're using. Like if you're using Desmos, you would actually use int x. Sometimes you'll see it as y equals, and you'll see square brackets around it, x. And then sometimes they also, depending on if it's an upper bound or lower bound, they also have floor and ceilings. So you'll see something that looks like that for a ceiling function and that for a floor function. But we're just going to worry about the regular step function. Okay, so the regular step function, the parent step function, looks like this. Okay, so if you remember, the greatest integer is basically if I put in a rational number, you want the next biggest integer. And that's why it's called the greatest integer. So what happens is your graph ends up looking like this. So that's like for 0. And this one would be for 1. And this one would be for 2. And this one would be, oops, let me make it that close. This one would be for -1, right? And so what you end up with are quite literally a bunch of steps. Okay, technically the domain and the range are both, oh no, I lied. The domain is all real numbers, and negative infinity to positive infinity. But the range only uses the set of, the set of integers. And that's why it's called the greatest integer function. There is a symbol for integers. It looks like that, which if you would like to use that, you can do that. It is obviously not continuous because it's in a million little pieces, so it's discontinuous. The only y-intercept is the origin. Oh, my pen's being weird. There we go. And then the x-intercepts are all of the numbers from 0. Oops. Let me rewrite this. I said it, but I didn't write it. From 0 to 1, uninclusive on that right side, because that's an open circle. So that's kind of weird, but those are the x and y intercepts. It is not symmetrical. It is not bounded. There are no maxes or mins. There are no asymptotes. And so the end behavior, actually this one actually does have end behavior. It's just kind of weird. I mean, it's not actually weird. It's just weird to think about. So on the right side of the function, on the left side. So on the left side of the function, if you think about it, those steps are going to keep going down. It goes to negative infinity. On the right side, those steps are going to keep going up. Pardon me. So that's going to be positive infinity. So let's see. I think I have it all. Maxes, mins, not bounded. Intercepts and behavior. Yep. I think that's all of them. Okay, so we have a logistic function left to do. And so this one is new. The logistic function looks like this. Oops, I didn't mean to write that. Let's go here. The logistic function. Okay, it's 1 over 1 plus e to the negative x power, which looks like a load of fun. And this is going to pop up actually later this chapter, and then a few more times during the year. So basically it's pretty straightforward as far as the graph. So I'm just going to go ahead and, so there is an asymptote at +1. Wow, let's change that. Here we go, an asymptote at +1 and an asymptote at -1. So that's going to help me sketch my graph a little bit, and it does go through the origin. So it sort of looks like a cubic function. Like it has that S shape that I can't draw very well. Let me turn my iPad sideways, maybe that'll help. Yeah, that didn't help a lot, but you get the idea. Except for the difference between that and the cubic function, wow, that sucks. Is that the cubic function doesn't have asymptotes. Wow, okay, let's try that again. So this one is obviously bounded. Okay, that's a little better. There we go. I'm satisfied with that one. Okay, so that's the logistic function. All right, the domain is all real numbers. The range is obviously not. It goes from -1 to +1, but since those are asymptotes, I need to make sure and use parentheses. The only x and y intercept is the origin. It is bounded above and below. It is continuous. It doesn't have any maxes or mins. Okay, my brain is turned off. What else do I need to do? The end behavior. There was something else. Oh, the asymptotes. Duh. I only said it like 5 times. The asymptotes, of course, are the line y equal 1 and y equal -1. Those are the two asymptotes. And that's actually my end behavior as well. They flatten out on both sides. So on the left side, the function evens out at -1, and on the right side, the function goes to +1, and that is the logistic function. And if I forgot something, you guys remind me tomorrow.